please, can you share that on your screen? I am having some difficulties to share my screen. So would you please share the screen back and open the link that I've shared it across to you. I've shared it across to you in Zoom. Right. So, sorry, I have some small disturbance in the backend. Apologies for that. Hey, good evening, everyone. This is Suraj, co-founder and CEO of Decibels Lab. Always a great pleasure to have people attending, to see people attending the sessions on batteries and battery pack or battery management systems or algorithms for battery packs and things like that. So that shows an interest that people have a good inclination towards the batteries and battery pack and BMS and stuff like that. So good to hear from all of your side, and good to see your interest and enthusiasm to take part in this courses or boot camps that we are hosting. So by the way, before we get started for the boot camp, so we just wanted to give you an intro on what is this boot camp, and then I will hand over the session to Abhinav. I would not chew much of the time. So most of the sessions can be and will be handled by Abhinav on the technical sides of it. So this is basically a 3-day program, and which happens over an online module, like a live Zoom sessions or YouTube lectures that are being live streamed on YouTube. And every day we take up about an hour or about an hour and a half, depending upon the learner interactions, to cover up some of the fundamental topics on lithium-ion cell chemistries and also on the characteristics of lithium-ion cells, right? So if we go below Abhinav, so on the day-wise details, can we go a little below? Yeah. So here are the topics that we are expected to cover as a part of this bootcamp. So first day, that is today, as a first day of the bootcamp, so we will be covering on foundation to electrochemical cells and the reactions. So here we talk about overview of cell chemistries, again, fundamental cell chemistries and some of the new chemistries and the lithium as well. And then the discussions will move into electrochemical reactions with one of the example as a cell. And then we'll go to understand certain pros and cons of the lithium-ion cells. So what are you going to learn out of this today's session? You will understand a different type of chemistries, their comparative differences, and then we will go a little deeper to understand the reactions that happens at the cell, and where Abhinav will get you through certain hand calculation things and details of the internal studies, so that you could get an idea fairly in terms of a chemical level. And then we move to our next day, that is tomorrow. We'll work on certain areas such as voltage calculations for nominal voltage and a capacity. Again, that will be a hands-on activity where you have to have pen and paper. You could also do the calculation along with Abhinav, so that you will be able to get through the content very well. At the last day, there will be a detailed discussions on testing and characterization. Let's say we have a cell, or we're going to build a cell. How do we ensure that we get the data from the cell? So the data is basically, okay, I'm targeting about 2000 mAh for a cell, but do I have a 2000 mAh at a given available discharge current? Do I have it at available discharge temperatures? How exactly these curves come? Okay, so we would look little interesting details on some specific cell chemistries. Maybe we'll conduct some test data on LFP, maybe some other cell chemistries, so that we can show you a data how the cell looks, how the characteristics of the cell looks slightly different for each type of cell chemistry, and also how do we do like further advanced tests like HPCC or DCIR. So that's the overall idea, what we're going to cover in 3 days. So you have to be a part of this complete 3-day live lectures to get the certificates. So we will be sharing you a certificate of participation for attending the complete 3-day program. So how do you get it? So you have to mandatorily basically attend everyday class for 3 days. And the last day, we will be sharing you the link in the live classes to generate your certificates. All right. And so you can expect that by end of the sessions or bootcamp, you would have a fair overview knowledge of batteries, cells, and cell chemistries, and some of the calculations for certain cells. And also, we will give you some assignments that you can also practice and come back. And then you'll also understand how does a cell behave with areas of capacity and cycle life, and few other tests for characterization as well. Great. So to deliver this lecture, so we have Mr. Abhinav, who is our team member at Decibels Lab, who take care of creating a lot of content around on cells, batteries, and chemistries and things like that. So by the way, Abhinav is a graduate in mechanical engineering. So he's a graduate from automotive engineering from the background at Hans, Netherlands. So he is working at Decibels for about a year now. He takes care of a lot of areas of battery simulations, model-based design, algorithm development, real-time testing, data validation, prediction models. A lot of these things what Abhinav works today at Decibels Lab. So as a great person by his knowledge, and would be glad to share his the knowledge that he has gained over a couple of years being in the in academia, also in the industry as well. So over to you, Abhinav, for taking care of the rest of the session. Thank you.
Thank you, sir, for the introduction. So a very warm evening to everyone. So welcome to this session on Foundation to Electrochemical Cells and their reactions. So in this session, so as Suraj sir had briefly explained before, we'll be taking a look at what exactly are electrochemical cells, right? And what are some of the important internal structures? What is some of the components that contribute to a cell? And briefly, what are their functions? And then we'll be looking at some of the prime examples of an electrochemical cell. What are the reactions that happen inside? And some examples of some different chemistries like lead acid, nickel cadmium, nickel metal hydride, and lithium ion cell. Yeah. So we'll be briefly taking a look at all of these. Yeah. Then we'll compare some of the properties of each of these chemistries, and we'll understand as to which cell dominates the market as of today and why that is so. And then finally, some properties, some advantages and some disadvantages of a lithium ion cell, and exactly why it is currently preferred and why exactly it has such a good preference over so many other cells. Yeah. So yeah, with that, let's get started with our first topic. That will be on understanding what are the different energy storage devices. So before we jump into batteries and cells, let's first look into briefly what are the different energy storage devices. So yeah, the first one which we see, this one, the flywheels, these are rotational elements and they provide rotational energy. So basically what they do, they store rotational kinetic energy and convert it into useful mechanical energy as and when desired. So one good example of this would be in your IC engines, where you have flywheels that store some rotational energy, right? And we are able to maintain the engine's performance throughout, and also keeps the performance balanced. Yeah. So flywheels basically are rotational storage devices, rotational energy storage devices. Yeah. So that is for flywheels. And if you come to hydroelectric dams, so hydroelectric dams are basically storage devices that can store water at a particular height. And when that water is released, it can strike a turbine or rotate some turbine fan or some blades, which can then provide electricity. Or even then, the energy can be stored in a separate reservoir. Yeah. So this is another form of energy storage devices. And one more would be with respect to magnetic energy. So we know a very good example of magnetic energy device, that is a transformer, right? So it can convert electrical energy to magnetic energy, store it in the transformer, and then release it when necessary using induction coils. Yeah. So basically, inductor coils are being used here. And with that coil, some amount of magnetic energy can be converted to electrical energy and then released. Yeah. So especially in large power plants or in industries where a huge amount of energy has to be converted into magnetic energy and stored. Yeah, that's where these kind of devices can be used. And then finally, we also have electrochemical devices, right? So here is where chemical energy will be utilized and it will be converted to electrical energy as and when needed. Yeah. So in the form of chemical reactions that occur inside the cell, electricity can be generated. Yeah. So this is what is called as a battery. So a group of cells forms a battery. So these are the different energy storage devices that one would encounter in today's modern world. So there are some others, some other as well. Okay, some of them others would be ultra capacitors. So ultra capacitors have a similar function as to what magnetic energy storage devices have. So instead of storing it in terms of magnetic energy, it would store it in terms of electrical energy, and then release it whenever needed. Yeah. And also we also have air compressors. Air compressors are also energy storing devices. They're basically auxiliary storage devices, which would first convert air compressor air into some storable compressed air storage energy, and then convert it into useful mechanical power to drive any device whenever the power demand is required. Yeah. So just like so, these are the different examples of energy storage devices. Yeah. So now our focus will be towards electrochemical cells. Yeah. So where we look exactly as to what an electrochemical cell is, some of its components, how it works, and some of the respective reactions. Yeah. So now, what exactly is an electrochemical cell? So as I had said, it is a device that can store energy and also produce energy, basically with respect to chemical energy. So we know some amount of chemicals will be used in the cells, and that chemicals will then undergo some reactions, and that reaction will then be used to convert chemical energy to electrical energy, or reverse it by using electrical energy to convert it to chemical energy. Yeah. So basically charging and then discharging. So that's exactly what happens in a cell. So while discharging, you're converting chemical energy to electrical energy, and while charging, you do the opposite. So you'd be converting electrical to chemical energy. Yeah. So this is exactly what is an electrochemical cell. uh, so here you can just see some pretty common examples. So lead acid batteries, we know a very good example where lead acid batteries are used in our common road vehicles in today's world. So this lead acid battery is used to start the motor, the starter motor, which then starts the engine. Yeah. And then these are pouch cells. Okay, so this is a pouch cell, and these pouch cells can be used in mobile phones, it can be used in laptops, smartwatches. They're even used in modern day electronic equipments, and even in electric vehicles where size has to be reduced, the size of the battery has to be reduced, and very compact form of batteries, yeah, can be used. And this is exactly where pouch cells are used. Yeah. And then these are lithium ion cells, and the bottom over here, these are lithium ion cylindrical cells. So uh, they are of the similar composition as to a pouch type cell, but their form factor is a little bit different, right? And of course, some of their chemical properties would also differ. Yeah? Things like nominal voltage, their weight, energy density, and all these. Yeah. And then here you can see a double A nickel nickel metal hydride battery. It's a Duracell cell. And here, this is our everyday usage battery, which you would probably use in your clocks or watches, your calculators, your handheld electrical devices, blood pressure monitoring instruments, things like these. Yeah. So yeah, these are just some of the common examples that you'd see of batteries today. And this is how you define an electrochemical cell. Yeah. So now we'll come into electrochemical cell classification. So how exactly will we classify an electrochemical cell. So basically, we will classify them into two main categories. So one would be an electrolytic cell, right? And the other one would be a galvanic cell. So in the previous slide, we saw the definition of an electrochemical cell. Basically, it is a device that can convert chemical energy to electrical energy, which is exactly what is a galvanic cell. A galvanic cell converts chemical energy, stored chemical energy, to electrical energy. Okay, so in many of the cases, galvanic cell reactions, that is chemical to electrical, is non-reversible. Okay, which is why it is called as a primary cell. Okay, so that example that we saw of a Duracell battery, right? Those kind of cells are non-rechargeable. So which means once you use them, they cannot be reused, they cannot be recharged. The chemical reactions or the chemical energy inside cannot be obtained back, and it cannot be replenished as such. Yeah, so it has to be disposed once all of the chemical components inside, or the chemical composition inside, has been used up. Yeah, so this is what is a galvanic cell. Okay, so this is chemical to electrical energy. Another classification is electrolytic cell, where it is electrical to chemical. Okay, so electrical to chemical energy is where you'd be supplying a particular device that already has some chemical energy stored inside it, or some chemical compounds stored inside. And once electricity is supplied, these chemicals will undergo reactions to give some sort of byproducts. Uh, and one very good example of this kind of a cell is where you might have heard of this process called as electrolysis. Yeah, so where you have jewelry equipment which is dipped in some sort of a chemical solution or some sort of a chemical bath. Yeah, and once electricity is supplied to that bath, we'll see that some amount of material or some amount of some amount of layer of gold or silver has been deposited onto that jewelry item. Yeah, so that is exactly what is an electrolytic cell. Basically, it undergoes some chemical reactions because of electricity being supplied to it, and from those reactions, we'll obtain some compounds or byproducts. Okay, another good example would be hydrogen fuel cell, right, where water splits up into hydrogen H and oxygen, right? So this hydrogen will further be used for combustion. So this is exactly what is a fuel cell. It basically undergoes electrolysis, water undergoes electrolysis, and then forms hydrogen plus oxygen. So this is a simple understanding of the classification of an electrochemical cell, right? Now, these two concepts, these two, methodologies of an electrochemical cell, if you combine them together, if you combine the working of an electrolytic cell and if you combine the working of a galvanic cell, you get a secondary cell. Okay, so what that means is that it is capable of producing electrical energy from chemical energy, and also it is able to replenish its chemical energy by receiving electricity. Yeah, so that is basically what is called as a rechargeable cell. So all your modern equipments, your smartphones, your laptops, even your electric vehicles, all of them have secondary cells, which means they're rechargeable. Yeah. So basically, whatever energy or whatever chemical reactions are happening inside can be reversed. Okay. So this is how broadly we'll classify electrochemical cell. Yeah. So now with respect to this classification, we will now look into some of the cell components. Yeah, so these are some of the important components inside of a cell. So on the left hand side here, you can see a diagram of a nickel zinc cell. Okay, a nickel zinc cell. Okay, so this is a simple uh, primary type cell. Okay, so it's not really a rechargeable type cell. And here you can see anode and cathode. So this portion over here, this red wall that we see, this is the anode, yeah, and this portion just next to this, just next to the anode over here, the gray portion over here, this is the cathode. Okay, and in between the anode and the cathode, there will be something called as a separator. Okay, so your anode will be your negative terminal, okay, and your cathode will be your positive terminal. So always, this is usually the sign convention that's followed. Yeah, and separator is a sort of insulation wall that is provided in between the anode and the cathode, so that if in case the anode and cathode do touch each other, or when they come in contact, short circuit can happen inside the cell, or basically the cell can explode. Okay, so for that purpose, for a separator will be provided. It's basically an insulating wall that's made out of like rubber, okay, some sort of a rubber or some sort of a plastic coated with oil. So these are the most commonly used materials for a separator. Basically, it has to act as a insulator so that your anode and your cathode don't touch each other, and so that they don't cause an explosive reaction inside the cell. Yeah. So we know that some chemical reaction happens inside the cell, right? So this chemical reaction has to happen between the anode and the cathode. Okay, so the chemical reaction always occurs between the anode and the cathode, and for that purpose, an electrolyte will be used. Okay, so an electrolyte is basically a conductive medium. So this gray portion that you see over here, this complete gray portion, this is called the electrolyte. Yeah, and this electrolyte is basically a conductive medium. This allows certain reactions to allow ions to flow between the anode and cathode. So there is some amount of ionic flow. Some ions have to flow between the anode and cathode during the reactions. Yeah, and that has to happen through the electrolyte. Okay, and so that is exactly the function of the electrolyte. It has to allow those ions to flow freely and smoothly without any resistance, any problems, or any hindrances. Yeah. So once these ions are flowing between the reactions, they have to start producing some amount of power. Yeah, that happens through the current collector, and that is exactly what uh, this green component that you see here. This is the current collector. Yeah. So this basically current collector acts as a connection between the electrolyte and the positive terminal, the external port of the battery. Yeah. So this current collector will then allow the ions to flow freely outside the battery into the power, into the load. Yeah. So to whatever load or whatever equipment is there that is requiring some power, that is drawing some power from the battery, all your ions will flow through the current collector over here into the positive terminal and then out into the load. Yeah. So that is the function of the current collector. The sealing ring is a device that simply keeps the chemicals inside the battery. So basically, it should not leak outside the battery. Otherwise, it can cause some toxic harm to people. It can cause some damage to the environment. So in order to prevent any leakage from happening from inside the cell to the outside of the cell, or to prevent any dust from entering into the cell, so for that reason, sealing ring will be used. And then, yeah, we have positive and then negative terminal. Yeah. So the current collector then extends out into the positive terminal. So up here, this is a positive terminal where current is discharged from the cell. And then bottom over here, this is the negative terminal where current is received. Okay. So whatever is being released from the cell has to complete the circuit, right? So it has to flow through the load and then it is received back into the negative terminal. Yeah. So this is the complete cell components, and these are the working of each and every component in brief. Yeah. So with this, we will now move on to the next slide. Okay. So here we have primary reactions in a cell. So as I had mentioned earlier, so there'll be some amount of reactions that occur. So primarily, the reactions that occur in a cell will be oxidation and reduction. Okay, so let's take a simple example. Say a Daniel cell. Okay, so basically a Daniel cell, it was a simple electrochemical cell like this, which was invented in the year 1836. Okay, so it was basically consisting of two simple metals, zinc and copper. Okay, so the zinc metal that you see, this was the anode. Okay, and this will be the negative terminal of the cell. Okay, and copper here will be the cathode. Okay, and this here will be the positive side. Okay, so when this cell is constructed, it is not just zinc and copper that act as the anode and cathode, right? So it has to be put into some sort of a salt bath. Okay, and that salt bath is exactly what is the electrolyte. Yeah, so your electrolyte is usually some sort of a sulfate salt, so zinc sulfate. Okay, so this will be your electrolyte. Okay, so your electrolyte will be basically a salt solution or some sort of a fluid solution which will be filled for both the anode and the cathode material. Okay, and they're kept individually in two separate containers connected by what is called as a salt bridge. Okay, so this is a salt bridge. Okay, so this green colored sort of structure that you see over here, this one, this is called as a salt bridge. Okay, and basically it acts as a connection between the anode and the cathode. Okay, so in simple terms, what happens is when a load is connected to this kind of a setup, so basically these are wires. Okay, these are wires that connect to the load, and when these wires are connected and when the load is given to the cell, what happens is two reactions occur simultaneously. One is called oxidation at the anode and reduction at the cathode. Okay, so here you can see in this animation, zinc undergoes oxidation. So what that means is zinc separates into zinc ion and it releases two electrons. So that's what is oxidation. Basically, oxidation is releasing electrons. Yeah, so releasing electrons is oxidation. Yeah? And reduction will be to absorb these electrons which has been released from the anode. Okay, so here you can see whatever electrons has been released here from the zinc anode. So that particular those particular electrons will then go towards the cathode, right, which is copper, and then it will combine with the copper ions there to give you copper. Okay, so whatever copper ions we have combined with those electrons will give copper. Yeah, so these are the simple reactions that takes place. It's called oxidation. And this is reduction. Yeah, so basically these are the different reactions that occur inside a cell. Yeah, so collectively these reactions are called redox reactions. Yeah, and they have to occur at the same time inside the cell. They have to occur simultaneously so that there is no charge imbalance, or there are no ions left out, or there is no reactions that are left incomplete. Yeah, so for that purpose, the redox reactions always occur simultaneously. Yeah, and this is how basically a simple electrochemical cell works. Okay, and this is an example of a Daniel cell. Okay, so with this, we will now move on to some other examples that we will see in the next slide. Okay, so this is here, you can see here, this is the complete set of reactions that occur in a Daniel cell. Yeah, so copper, this is your cathode, and then zinc is the anode. And here you can see as and when electrons flow from the zinc anode into the cathode, you can see that zinc ions are formed. Yeah, and these zinc ions have to flow towards the copper side, while copper ions have to flow towards the anode side. Yeah, in order to maintain charge balance. So charge balance or charge neutrality. Yeah, so charge neutrality has to be maintained. Yeah, so for that purpose, whatever zinc ions are being generated here at the anode will flow through the salt bridge towards the copper cathode, and whatever copper ions are being produced at the copper cathode will flow through the salt bridge towards the zinc anode. Yeah, so this is how the circuit is completed, and this is how this particular electrochemical cell works. Yeah, so here you can see how exactly reduction happens and how exactly oxidation happens. Yeah, and these potential values that you see here, yeah, this 0.34 volts and 0.76 volts, so these are obtained through something called as electrode potential charts. Yeah, this is something which we will be looking to tomorrow's session, where exactly we'll be referring to a electrode potential chart, and we'll arrive at the total cell potential. Yeah, so this is tomorrow's session. But overall, you can see here, this is the reduction reaction and this is the oxidation reaction. And when you put the two equations together, or when you put the two reactions together, you get something called as the redox reaction. Okay, so this final equation that you see here, this is called redox. Okay, so this is called as the redox reaction. So this is how the redox reaction occurs overall. Yeah. So basically how this happens, if you combine the two reactions put together, yes, say for example, we have the oxidation reaction. So let's write that down. So let's say I have oxidation. So let me just make some space here. So let's say I have oxidation, which I'll just write as OX. Yeah. So this is going to be zinc splits into zinc ion plus 2 electrons. Yeah. And then let's say I have reduction reaction. So that I will write as RED. So RED is nothing but reduction. Copper ion plus 2 electrons gives copper. Yeah. So if I add these two reactions together, yeah, if I add these two reactions together, what do I get? I get this final reaction. So zinc plus copper ion, yeah, gives zinc ion plus copper. Yeah. And if you see here, the reason why 2 electrons won't come into this final equation is because whatever electron is being released here in the oxidation reaction will be absorbed here during the reduction reaction. So basically it's like they are canceling each other out. Yeah. So you can just go ahead and you can just cancel these two out. So all you'll have left is zinc plus copper ion gives zinc ion plus copper. So basically this is what is called as a reduction reaction. And these are the primary governing reactions that occur inside a cell. So whichever cell you consider, whether it's a Daniel cell like this, or whether it's a lithium ion cell, or whether it's a lead acid battery, whatever battery it is you have, or whatever cell it is you have, this is the kind of primary reactions, or these are the kind of redox reactions that will occur inside the cell. Yeah. So this is with respect to all of the reactions that occur in the cell. So now we can take a look at some of the different cell chemistries that we have very well established in today's market. So first and foremost, probably one of the most famous examples is a lead acid battery. Okay, so the reason why this is called as a lead acid battery is because it uses sulfuric acid as the electrolyte and lead as an anode. So basically it's lead, okay, and sulfuric acid, which is H2SO4. Okay, so we know that oxidation is nothing but losing electrons at the anode. So we know lead is the anode. So if lead undergoes oxidation, it becomes lead, okay, plus sulfate. Okay, so basically what happens when lead undergoes oxidation, lead ions are formed, and immediately lead ion will go and combine with the sulfate ion. So therefore it becomes lead sulfate, and it releases hydrogen plus 2 electrons. Okay, so this is basically your reaction that occurs at the anode. So basically this is your oxidation reaction. Yeah, so this is your oxidation reaction, and likewise let's have the reduction reaction here. Reduction reaction is basically your cathode undergoing reduction. So cathode is lead oxide, which is PbO2. Okay, so plus 2 electrons plus H2SO4. So the electrolyte reacts with both the anode and the cathode. So once again here, lead sulfate is formed. So PbSO4 plus H2O. Okay, so water becomes a byproduct here, and this is your reduction reaction. So basically, this is what happens during discharge. So if you discharge the cell, or if the cell starts to provide current at the terminals, then basically this is the reaction that will occur. Yeah. So reduction and oxidation at cathode and anode respectively. And if you were to consider charging, yeah, if you were to consider charging, or when the battery is receiving electrical energy, so basically it would reverse the reaction. So what would happen? Your right hand side reactions, so whatever you have on the right hand side of these reactions comes to the left hand side, and likewise left hand side goes to the right hand side. Okay, so basically, so you can just write this down here. So this is during discharge. Yeah, and then if you were to charge this battery, you would have the opposite of this. Yeah, so it's pretty simple, and this is the simplest reaction. Of course, this is not a balanced reaction. In order to balance it, you would have to consider how many moles are present and how many electrons, and the amount of substance being used, and as such. But I will not be going too much in depth into that. You just have to know that this is your discharge reaction. And in the lead acid battery, this is the reaction that occurs. Yeah. So this is your typical lead acid battery equation, right? And if you were to consider its voltage that it produces, a typical lead acid cell, just a single cell, would produce you somewhere close to about 2 volts to something like 2.2 volts. Yeah. So one cell would give you about 2.2 volts. And if you were to combine it into a battery, it would give you something almost like 14 volts. Yeah. So if a car battery usually produces somewhere close to around 14 volts. It's not 12 volts, it's 14 volts because it has to stay above the minimum required voltage of all of the electrical components. Yeah. So usually somewhere around 7 individual lead acid cells will be used in a car battery, which collectively produces close to 14 volts. Yeah. So anything around 14 volts or close to 14 volts is considered to be a healthy lead acid battery. But you know that over time, as and when it starts to like degrade, as and when the number of years passes by, we'll see that the voltage reading starts to deplete and it goes below 13. So that's when we know, okay, yeah, the lead acid battery needs to be replaced. Yeah. So this is basically the kind of reaction that you'd expect in a lead acid battery. Yeah. And for nickel metal hydride, again, along the same principles, you would have an anode made out of any metal hydride. So basically, the metal is chosen depending upon what kind of reactions or what kind of properties is wanted. Again, it's based on the manufacturer requirement. Yeah. So it could be like potassium, it could be zinc, it could be manganese, magnesium, it could be any of these metals. And as I said, depending upon the requirement. So again, as I said, metal hydride, so that will be generally given as MH. Okay, so metal hydride will undergo oxidation. So what we'll have? We'll have pure metal, a metal ion, plus a hydride ion, right? Plus an electron. Okay, so again, of course, depending upon what is the composition over here, right? Whether it is more number of metal ions than the hydride ions, or more number of hydride ions than the metal ions, depending upon that many number of electrons will be given out. Yeah, so this is basic oxidation occurring at the anode. And at the cathode, we have nickel oxyhydroxide, which is the most common commonly used cathode material, yeah. So which is represented by nickel oxyhydroxide, so NiOOH. So you can see over here, yeah. So this will undergo reduction. Okay. So what will happen? This hydride ion will go and combine with this, and also the electrons will combine with this. So you will be found with nickel dihydroxide. Okay. So this is basically the reduction reaction occurring. So hydrogen plus 2 electrons will combine, right? And then finally it will form nickel dihydroxide. So this is your final reaction at the reduction side, and this is your oxidation. So you can just oxidation, and this is your reduction. Yeah. So these are your reactions that occur inside a nickel metal hydride cell. And then commonly you'd see that nickel metal hydride cells would give you somewhere around 1.4 to around 1.8 volts as your nominal voltage. So compared to a lead acid battery, it's much lower, which is why like nickel metal hydride is usually limited to like very low power applications, like in your wristwatches, or something like your calculators, or really small devices like, yeah. uh, so these are some of the chemistries. And also we have nickel cadmium, and also we have for lithium ion, yeah. So in similar terms to nickel metal hydride, we'll also have the similar reactions occurring in the nickel cadmium. So along the same side, so we have instead of having metal hydride, we will have uh, cadmium as the anode and nickel oxyhydroxide as the cathode, yeah. So just the same way as we saw metal hydride, except for metal hydride, cadmium will be getting will undergo oxidation. So it will form Cd plus hydroxide ion, right? It will give cadmium hydroxide plus electron. So this will be your anode reaction. And at your cathode, it will be nickel oxyhydroxide combining with the electron. Yeah. And another hydroxide ion to form nickel dihydroxide. Yeah. So basically, this is how your reaction would occur. This is pretty similar to what you would see in a nickel metal hydride cell as well. Yeah. So again, very close to about 1.6 volts is what you can expect from nickel cadmium cells. It is kind of low because again, your voltage is directly dependent on how many electrons is being produced. Yeah. So here, not many electrons are released during the reaction. So for that purpose, you will see that your voltage being produced from nickel cadmium cells is kind of low. Yeah. So again, this is restricted to like low power applications. And now coming to probably the most common example of today's electrical applications or electric device applications is lithium ion battery. So here you will see that the anode is made out of lithium carbide. Okay. And then cathode will be made out of some sort of a metal oxide with lithium. Okay. So some lithium metal oxide. So it could be lithium manganese or lithium cobalt, lithium aluminum, or such types of metal which could give you very good rates of reaction. Yeah. And then commonly used electrolyte would be your lithium hexafluorophosphate, so which is basically given by LiPF6. Okay. So again, in a similar fashion as to how you would have oxidation and reduction, your anode graphite, that is LiC6, okay, which is your anode material, lithium carbide, undergoes oxidation and it forms lithium ion plus C6 plus electron. Yeah. And in your cathode, where reduction happens, so you have lithium metal oxide, which I'm just going to write as lithium MO plus electron, right? And yeah, I'm sorry, this is an ion here. So LiMO plus lithium metal oxide ion plus electron will give lithium metal oxide. Yeah, LiMO2. So So this is how the reduction reaction in brief happens. Of course, like it again depends on what kind of metal is being used, what are its potential, what is its capability, and all of that. That is something which we'll be exploring in tomorrow's session. But these are the primary reactions that would occur inside a lithium ion cell. So generally, we see that today's lithium ion cells gives you roughly around 3.7 to about 3.8 volts. Yeah. So yeah, these are the this is your reduction and oxidation reaction that occurs inside a cell. And if you were to charge the battery, so whatever reaction you see here, this is during discharge. If you were to charge the battery, your reaction direction would reverse. So basically, it would your LHS and RHS would swap. Yeah. So generally, these are the different reactions that are considered in the lithium ion battery. Yeah. So now we have seen we have seen briefly what could be the reactions and what are some of the voltages being produced by each of these chemistries. Yeah. So here is the comparison between each and every type of cell chemistry. So from lithium ion, lead acid battery, nickel cadmium, and nickel zinc or nickel metal hydride. So nickel zinc even applies to nickel metal hydride. So what are the different properties you'd want to compare between each of these different types of cells? Yeah. So starting with lithium ion, so we can see the first and foremost parameter that everyone looks at, everyone today in today's market looks at, is the energy density, how much energy it can contain within a specific volume. So if you compare all of these, you can see that lithium ion is the highest. Okay. The reason for this is being in the amount of nickel content present inside. So higher the nickel content, higher the energy density. So that is sort of a established principle that nowadays everyone has been able to observe this, that more amount of nickel gives more amount of energy density. Yeah. So which actually is very useful in terms of electric vehicle applications. So you don't have to use too many cells in order to produce that much amount of power. So which is exactly why cells with higher energy density is preferred. Yeah. And then you can see how it is for lead acid battery and nickel cadmium. So again, it is dependent upon the rate of reaction and all of these. Yeah. Specific energy. So along the same lines, how much energy it can store per unit mass of the cell. Okay. So per kg of the cell or per gram of the cell, or such along these lines, how much energy it can store. So basically, again, this is the highest. Lithium ion is the highest. Again, the same reason is because of the amount of nickel present inside. Yeah. So the high, very high. So compared to all these chemistries, lithium ion has extremely high amounts of nickel. Yeah. So that is the contributing factor to very high amounts of energy present. Yeah. And efficiency. So the overall operational efficiency. So in terms of charging, in terms of discharging, and overall your lifespan for over several years, which gives you a very good efficiency of over 95%. Yeah. This is because of, again, your cathode and anode structures, the electrolyte properties, and overall the characteristics which the cell is able to retain over the entire usage time. Yeah. So 95% efficiency is what you can expect from lithium ion type cells. Yeah. And for lead acid battery, it is actually one of the poorest. So it undergoes extremely heavy losses, during operation, especially at slightly higher current values. You'll notice that its efficiency drops. Yeah. So coming to another parameter called self-discharge. Basically, self-discharge is a sort of parameter you would measure in cells in order to understand how much of its capacity or how much of its voltage is it permanently losing over an extended period of time. Yeah. So for example, let's say that we're trying to store a cell, or we're trying to store a battery in a certain condition. Yeah. So if you were to store a lithium ion cell compared to if you were to store a lead acid battery, a nickel cadmium, and a nickel metal hydride battery, these batteries would lose a large amount of capacity during that storage, while lithium ion would lose only less than 5% in storage period of a year. Yeah. So which is why nowadays lithium ions are so much preferred, because if we were to just leave the lithium ion battery in an open environment like this, we know, okay, yeah, that the battery would not discharge, it would not undergo severe losses, it would not lose all of its capacity, right? And then it would still be in very much a usable condition even after long extended period of storage. Yeah. So here you can see Number of cycles, so up to 3,000 cycles that are an average a lithium-ion cell can provide. Modern day numbers, can even expect it to go up to 4,000 to 5,000 cycles, but that depends on, again, the chemistry, and it comes at a certain cost as well. So up to 1,400 cycles from the lead acid battery, and very poor life cycle on the nickel type batteries. So on the cadmium, nickel, cadmium, and nickel zinc. So up to 1,000 and up to 800, simply because the materials inside simply cannot sustain itself over extended charging and discharging cycles. So for that reason, 1,000 is all you can expect from that. And then finally, coming to nominal voltage, we can see here what a significant difference there is. So 3.8 being offered from the lithium ion cell, again, thanks to the nickel being present, so the rate of reaction increases, and then you have a very high amount of voltage over here. Yeah, so you can compare it over here to all of the other types of chemistries, and clearly you have the advantage here on the lithium ion side. Yeah, so these are your properties of each type of cell chemistry, a brief overview of this. And coming to today's last topic, what are the advantages and the different advantages and disadvantages? So right away, we know that lithium ion cells have very high nominal voltage, thanks to the rate of reactions that occur inside, high energy density. So basically, higher energy density would mean lesser number of batteries or lesser number of cells, lesser cells inside a battery pack. So if you were to develop a battery pack for an electric vehicle, you would obviously go for a battery or a cell that has very high energy density, so that you can use lesser number of cells. Yeah. So that is one of the major advantages of this cell, seriously, because not many other cells or not many other chemistries offer this kind of a high energy density. Yeah. And then finally, coming to the other characteristic, which obviously any manufacturer would prefer, is low self discharge. Any type of cell must be able to retain its capacity over an extended period of time. Yeah. So lithium ion cells are very advantageous in that particular field. But on the disadvantages, we know that certain, like, lithium ion cells can catch fire. So basically, it's called thermal runaway, and this kind of a phenomenon is common in lithium ion cells, simply because of the high energy density it has. So even though it's an advantage, it can serve as a disadvantage as well. So especially, we know, when you try to operate lithium ion cells at very high temperatures, or if you try to operate them at high currents, then it has a very good chance of catching fire. So that particular situation is called thermal runaway. Yeah. And this can basically, like, damage not only the cell but the battery pack, and overall cause some pretty dangerous drawbacks to the entire vehicle as a whole. Yeah. So that is one of the major disadvantages of the cell. So this kind of an example is pretty commonly seen in terms of Ola electric vehicles. So Ola S Pro, that kind of a electric vehicle, we know that it continues. We've seen in recent news, we've seen that these battery packs just suddenly ignite, or suddenly burst into flames, right? So that's because of something called as thermal runaway, right? And another major disadvantage is something called as dendrites. So dendrites can form, and this is particularly seen especially at high current rates. Okay, if you were to operate the cell or the battery pack at very high current rates, so they could form something called as dendrites. And this example you would have probably seen in from the Samsung Note 7, it was released like a few years ago. And in that, the battery was defected in a way that if you were to charge and discharge it a certain number of times, dendrites would grow inside the battery pack. So dendrites are like molecular sort of like molecular branches that grow inside the cell from the anode. So the more number of times you charge and discharge it, the more the dendrite grows, and it can cause a short circuit. So that short circuit is exactly what caused that particular phone to blow up every time. So that is like it is like a very a problematic phenomenon that occurs especially in lithium ion cells. Yeah. So that serves as one of the major drawbacks. Another thing is expense. So it uses cobalt, which is actually a bit expensive to obtain. It's a bit expensive to mine. It's a bit expensive to process and finally manufacture as well, in terms of lithium ion applications. So when it comes to like EV applications, obviously you want to keep the cost down. So cost per kilowatt hour, you want to keep the value low. So in order to keep the value low, you have to use lower amount of cobalt. Okay. So basically, cobalt itself would make the entire lithium ion cell pretty expensive. So generally lithium ion cells are kind of expensive. Yeah. So that apart from that, we also have a limited life cycle. So even though I did mention that it has 2 to 3,000 life cycles, right? So if you were to use the cell incorrectly, or if you were to sort of abuse the cell, it would drop even lower to say about 1,200 cycles. So even though, as I had said, per 2,000 life cycles, which is probably, if you were to use the cell in very good conditions, it would give you about 2,000. Yes, but it would not give you this case in reality, because you would be using the cells in different conditions, in different atmospheres, in different like temperatures, and obviously like the cell, other the entire battery pack wouldn't be kept in perfect condition. So for that purpose, realistically speaking, it would give you something like 1,200 or something, say as an average of about 1,500 cycles. Yeah. So this is one of the other drawbacks of the lithium ion cells. And so to briefly summarize today's session, we saw what are the different energy storage devices. We saw what is an electrochemical cell. We saw its classification. We saw some of the electrochemical reactions that occur inside, so reduction and oxidation. We saw redox reaction, and then we saw some of the common chemical reactions that occur inside some of the most commonly used batteries, or some of the commonly used cells in today's market. And then we also compared some of the properties of all of the chemistry, all of the cell chemistries. And then we understood why lithium ion is preferred over so many other types of cells. Yeah. And then we have here the advantages and disadvantages. Yeah. So this is your brief overview of cell reactions and chemistries. And in tomorrow's session, we'll be doing some numericals. So where we'll be calculating some common terminologies or some common parameters like cell voltage, capacity, and energy. Yeah. So it will be we will be referring to something called as a standard reduction potential chart. So in that, we will be able to obtain what is the overall cell potential, and also totally what is the capacity that is being generated at each electrode, so at the anode and at the cathode. Yeah. So with that, we finish today's session. Thank you all for attending. So now it's time for Q&A. So if anybody has any questions, I think we can take them now.